Hello students, today I am going to discuss boundary condition for reflection and transmission. So in this if we simply consider an infinitely long string and its end is not attached somewhere, then when we give a disturbance to the string, then a wave which travels and it reaches to the other end, it doesn't depend on any kind of boundary conditions. But if the string is attached to some end, then the wave that travels through this particular string that is attached on the other side, that depends on some boundary conditions. So here we consider a string that is simply tied onto a second string. Okay, so we have two strings tied on one string is tied to the another one. So here tension T is same for both the strings, and mass per unit length mu is different, and that's why its velocities are also different, that is v1 and v2. So as we know that velocity is equals to square root of tension upon mass per unit length. So here we consider that the knot occurs at z equals to 0. So instant wave can be written as fi, that is function of zt, ai exponential iota k1 z minus omega t. This is for the reason z is less than 0. So coming in from the left, it comes rise to a reflected wave. So and the wave function for the reflected wave is fr, function of zt, and function of zt, and this is equals to ar exponential iota minus k1 z minus omega t, and this is also for the reason z is less than 0. So here this symbol, okay, it represents complex function, complex wave function, and the negative sign on in front of k1 is because the direction of the reflected wave is opposite to the incident wave. Okay, so after that, traveling back along string 1, okay, and in addition to this, a transmitted wave is also there, and its function is f of t, function of zt, at exponential iota k2 z minus omega t, and this is for reason z greater than 0. So see here, this is our incident pulse going through the string, and here this is this instant wave reaching here, reflected back, and this wave is transmitted pulse. So direction of reflected wave is inverse, opposite to the incident pulse, and transmitted pulse is go forward. Okay, so here instant wave is a sinusoidal oscillation that extends to z equals to minus infinity, and refracted and transmitted wave extend to z equals to plus infinity. So here all parts of the system are oscillating at the same frequency omega. So since velocities are different in the two strings, however the wavelengths and wave numbers are also different, so we have the relation lambda 1 upon lambda 2 equals to k2 upon k1 equals to v1 upon v2. So here we consider that incident and reflected waves are of infinite extent traveling on the same piece of string. So it will be difficult to differentiate that which wave is incident wave and which wave is reflected wave. So therefore we consider an incident wave of finite extent. Okay, as I show you in the diagram. So it says a pulse. So, and we know that no finite pulse is truly sinusoidal. So the waves in figure 1, it may look like sine functions, but they are not. They are little pieces, very small pieces of sine waves joined onto entirely different function. So this can be built up as a linear combination of two standard functions. So linear combination of function is represented as f complex functions at t equals to integral from minus infinity to plus infinity a complex function k exponential iota kz minus omega t dk, where omega is a function of k. So we have already discussed this diagram. Okay. So for a sinusoidal incident wave, the net disturbance can be written as, so we know that incident wave and reflected wave lies in the same region, that is z less than 0. So it for this reason total function is ai exponential iota k1z minus omega t plus ar exponential iota minus k1z minus omega t, and for z greater than 0 reason we have wave function at exponential iota k2z minus omega t. So at the joint, that is at z equals to 0, the displacement just slightly to the left must equal to displacement slightly to the right. Otherwise, the two strings there is the break between the two strings. So mathematically, we can say that here the function is continuous at z equals to 0. That means f 0 negative is left hand limit 0 negative t equals to f 0 positive t. So if the knot is of negligible mass, then the derivative of f must also be called, that is curly f by curly z at 0 negative equals to curly f by curly z at 0 positive. Okay, if this condition is not satisfied, there would be a net force on the knot and therefore an infinite acceleration. So we can see it here. So here we have discontinuous slope. We have force in two directions. Okay, and in continuous slope, so there is a force on the knot. So in this case we have a continuous slope and we have no force on the knot. So these boundary conditions, these both boundary conditions apply directly to the real wave function f z t. But the imaginary part of this f function, we know that exponential iota theta is cos theta plus iota sin theta. This is our real part and this is our imaginary part. Okay, so real part of the wave function differs from the imaginary part just by there is this replacement of cos theta and sin theta. Okay, so that means if real part obeys the boundary conditions and then imaginary part also obeys the boundary conditions, and therefore complex function also obeys the same boundary conditions, and these boundary conditions are f complex, that is a function of 0 minus t equals to f at 0 plus t, and curly f by curly z at 0 negative equals to curly f by curly z at 0 positive. Okay, so we are going to apply these boundary conditions to the to our wave function. So from equation 4 we can write it as that f0 negative t equals to f0 positive t. So and in place of z we are putting the value 0, and for z less than 0 we have wave function ai plus ar. So we can see it as here. So for z less than 0 we have function this, and for z greater than 0 we have so in left hand side limit we are taking this function, that is for reason z less than 0, and for right hand side we have to take this function at exponential k to z minus omega t for reason z greater than 0. Okay, so on solving we get this, and on further solving this equation number 8 comes out this value ai plus ar exponential minus iota omega t equals to exponential minus iota omega t at. This is a result of first boundary condition when applied on the function, and second boundary condition is derivative of function at the left hand limit equals to derivative of function at right hand limit. So first we are going to find the value of derivative. For left hand limit we have taken the function for region z less than 0. Okay, so when we are taking derivative, we know that the derivative of exponential function is exponential function itself and the constant of the variable, that is iota and k1. So here we have a I exponential iota k1 z minus omega t into iota k1 plus a r exponential iota minus k1 z minus omega t, and its sorry, and its coefficient minus iota k1. So at 0 negative. So now we applying the limit. It becomes a I exponential iota 0 minus omega t iota k1 plus ar exponential iota 0 minus omega t, and finally we get the value, this one iota k1 and also exponential minus iota omega t, taking it common, and in brackets we have ai minus ar, and on we're also solving the right hand side. Okay, it comes out to be, similarly it comes out to be 80 exponential minus iota omega t iota k2. So using boundary condition that derivative of f with respect to z at 0 negative equals to derivative of f at with respect to z at 0 positive are equal. So we're well putting the values and we get that k1 ai minus ar equals to k2 80. Okay, and this is our previous result that functions are equal at left hand limit and right hand limit. So we have two equations now. Equation 1 is first is k1 into ai minus ar equals to k2 80, and second equation is ai plus ar equals to 80. So we have to solve these equations to find the values of 80 and ar in terms of ai. So when we adding the two equations, ar have opposite signs, it cancels out and it becomes 2ai, and here we have k2 upon k1 80 plus 80. So taking 80 common, we have this one 2ai1 equals to k2 upon k1 plus 1 80. So it becomes, on taking LCM, k2 plus k1 upon k1 into 80. So 80, on rearranging the terms, we have 80 equals to 2 k1 upon k1 plus k2 ai. So secondly, we're subtracting the same two equations, and on subtracting what we get, we are now solving it for ar. So 80 and 80 cancels out, and here we have ai minus k1 by k2 ai. So we have taken ai common, and in brackets we have 1 minus k1 by k2, and similarly here negative and negative it turns to be positive. So ar into 1 plus k2 by k1. So from this, on rearranging, we get the value of ar k1 minus k2 upon k1 plus k2 into ai. So in terms of velocities, we know that k2 upon k1 equals to v1 upon v2. So we dividing numerator and denominator by k1, and we get 1 minus k2 upon k1, 1 plus k2 upon k1. So value of k2 upon k1 is v1 upon v2. So we're putting this result and we'll get the value in terms of velocities. So ar is equals to v2 minus v1 upon v2 plus v1 ai, and at is equals to 2v2 upon v1 plus v2 ai. So we get the value of ar and at in terms of ai. So real amplitude and phases then are related by this term, real term. AR exponential iota delta r equals to v2 minus v1 upon v2 plus v1 ai exponential iota delta I, and at exponential iota delta t equals to 2v2 upon v2 plus v1 ai exponential iota delta I. So here we have two cases. If our second string is lighter than the first, that means mass per unit length of the second string is less than the mass per unit length of first string, so that velocity v2 is greater than v1. So all the three waves have same phase angle, that is delta r equals to delta t equals to delta I, and the outgoing amplitudes are ar is equals to v2 minus v1 upon v2 plus v1 into ai, and at equals to 2v2 upon v2 plus v1 into ai. And second case, if the second string is heavier than the first one, that is mass per unit length of the second string is greater than the mass per unit length of the first string, so that velocity v2 is less than v1, so the reflected wave in this case is out of phase, that is by 180 degree. So in this case, delta r plus pi equals to delta t equals to delta I. So we know that cos minus k1z minus omega t plus delta I minus pi is equals to cos minus k1z minus omega t plus delta I. Okay, so the reflected wave is upside down, so the amplitudes in this case are AR is equals to V1 minus V2 upon V1 plus V2 AI, and AT equals to 2V2 upon V2 plus V1 AI. So in particular, if the string second string is infinitely massive, that is very very heavy, or if the first string is simply nailed down at the end, then AR is equals to AI and AT equals to 0. In this case, there is no transmitted wave. All of the wave is reflected back. So this is all about the boundary conditions for reflection and transmission.